Hello everybody, welcome. In this episode we are going to talk about actions. We'll continue where we stopped in the last episode. We defined an editor, so now we know how to define an editor for statements. But editor contains a static definition of the editor, mostly static. It defines how components should be laid out on the screen. But you also need to customize the dynamic behavior of the editor. For example, you would like to be able to prepend logical expressions with not, if I delete not here. Now we've got a condition heading south, while heading south. If I want to say while not heading south, I need to convert the logical expression here into not, and then the logical expression here. So if I type not to the left from the heading word, it's recognized as an intent to create a not expression, and so not expression is created, and it wraps the original condition, and the not is then inserted into the while statement on the place where the condition was before. Also, you might want to convert while into if. So typing if, again to the left from while, will convert it. And typing while will convert if back to while. So again, this is dynamic behavior that is being defined in the actions. A few more examples. If you type and here after south, you get an end inserted. So an end logical expression, the left child of which is the original condition, and now the right cell is empty, and now I'm supposed to provide condition, the right child, myself. So again, that was sort of transformation which went from this condition to this condition. Well, another dynamic behavior, you might want to replace and with or. Just by typing or and completing, you want to replace the and with or. So now you change the concept, right? It's not a mere change in the editor, it's a change of the concept in the AST. We were replacing and with or. Okay, so how are these defined? In the actions here, we define the active or dynamic behavior of the editor. And we've got several ways we can define, and I'll name the most important ones. So we can create node factories, substitute actions, transform menu actions, and that's the core. These are the ones that we'll look at. So let's start first with not. So I was showing the example where you prepend not to the left of a logical expression and you get not created. So this is being defined in this site transform action. Site transform actions serve the purpose of transforming the AST if you type something to the left or to the right of an existing node in the editor. So in a cell left, if you are positioned to the left or to the right from a particular cell. Now if you type something, if it's matched against not in our case, then something happens. So here we say, if you are to the left from a logical expression, and the logical expression is not a not, so it's not an instance of not already, so you can't type not to the left of not. Nothing will happen in that case. So if I type not, no, I can't really type not here at all. So in that case, if you type not, this will happen. A new not node will be created, and it will replace source node, and source node is the logical expression to the left of which you typed not. So it's being replaced, and the source node is then set as the original for the not node. So in a not definition, the not refers to some wrapped condition, and that becomes the node that we transformed away. So that's what we replaced with not. Okay, another example of site transformation. Now typing if next to while will change while to if, and vice versa. While to if. Here is, again, a left side transformation. That's only applicable to a while, and if you type if to the left of while, then this happens. The while command, the source node, is replaced with an if statement. And we return the condition of the if. This is how we ensure that the cursor is then positioned on the condition, because that's the node we return. So MPS will set cursor by default there. There are other ways that you could change the selection after transformation, but we won't look into those in this introductory screencast. Now there's one thing that you might be wondering now. How comes that the condition and the body are preserved? I type if, and the whole statement changes, the whole command changes, but the condition and body, they stay. So the AST was transformed from a while statement with nested condition and body to if statement with nested condition and true branch, and true branch happens to contain the same commands that the original body of the while command. How did this happen? Well, there are two options. The first one, well, we could manually set it here. So we could say if node condition, give it the condition of the while node condition. So we would assign the original condition to the if statement. However, we would have to repeat that in all places where we convert nodes from if to while and back. So there's a universal solution called node factories, and we have a node factory here. Here we go. So that's another type of root concept you can create in actions. So here you simply specify construction code for individual concepts. You know, you might be tempted to add such code into the initialization code into the constructor of an if statement, for example. You know, in the behavior, if you create behavior for an if statement, now you might be tempted to write initialization code in the constructor, but that's a wrong place to put it, because the constructor is being called too early for doing anything useful. You can't really check the surrounding of the node like parent of the node, because it doesn't exist at the moment. The node is in the when you are inside a constructor, the node is being created. It's not part of an AST, so it has no parent, no descendants. It has no notion of the node that it is replacing, so you can't really do much useful stuff in the constructor. But you can do useful stuff in node factories, because here the node for if statement has been already created, and now it's being added to the AST. So you have access. So you have access to the enclosing node, which is the node that will be the parent of the if statement as soon as it becomes part of the AST. Then new node, that is the if statement that we're creating, and a sample node, if it's not null, is the node that we are replacing, so a while command in our case. So we have access to the tree where where the if statement will be inserted. We have access to the original node that was in the tree. So now we can customize the new node here. So in our case, we'll check whether the sample node is while command, and if it is, then we'll copy the condition and the body so that we initialize the if statement properly. In the same way we initialize while if we're converting from an if statement. Okay, one additional useful trick. Adding the else branch. You type else, and now you have an else branch where you can type some more commands. The else branch wasn't there, but simply by typing else, it appears on the screen. And notice the cursor is positioned on an empty line, and it is an instance of the empty line concept. So this is done again through transformations. This time it's a write transformation. So it's write transformation applicable to an if statement that has an empty false branch, so there's no else branch yet in the if statement. And in that case, if you type else, we add an empty line to the false branch, so it's no longer empty, so it appears on the screen. Remember, the editor for if statement shows the else branch if the false branch is not empty. So once we add an empty line to it, it becomes non-empty, and so it appears on the screen. Well, and again we return the first line of the commands in the false branch so that the cursor is positioned there. Now also notice this tag stuff here. There are several options for tags. Default is the default known tag, but you can then specify up to 5 tags associated with the action, and MPS ensures that the tag defined in the action matches with the tag defined for a cell. So the end cell here in the if statement is also marked with ext1, so that this right transformation is applicable to the cells tagged with ext1. There's only one such cell in the editor, and this one, so only to the right from this particular cell this action has effect, otherwise it's ignored. So it's only applicable after this first end. Nowhere else you can type else to have the else branch show up on the screen. Okay, now something a little bit more involved. Now I'm positioned to the left of a logical expression, and I type another logical expression, let's say heading south. So the original logical expression was replaced with a new one. Now I can position again to the left from heading south and type wall ahead, and now I get wall ahead instead. Now how this is done. So clearly we have a left transform action here defined for all possible logical expressions. So whichever we pick, like mark or wall ahead, they are all accepted. But that would be quite a tedious work if we had to define them all one by one. That's why we have parameterized actions in MPS. So this is the place. Here we say we have got a left transform action for logical expression. The output will be again a logical expression, and now we've got multiple of these transformations, one for each of these words: heading, mark, full, wall, and looking. So for all these, we've got an action. So this is the place where we define parameter objects. They are of type string because we want strings here. Now the matching text, what the user is supposed to type to initialize, to invoke the particular action, is equal to the string that we have in the parameters, in our case. Well, and then if the user types something, then here is the code that tries to detect which word was typed and then react to it. So if the user types mark, the new isMark command expression is created and then used to replace whatever the original logical expression was. Now to AND and OR. So if you have an AND, you can replace it with OR just by typing OR. So the action for this is defined in the language extension. And here we have substitute actions. Substitute actions are slightly different from transform actions. Substitute actions define substitution between nodes, so how one node can be replaced with another, and when. So this is the place where we define that AND and OR can replace one another. But to give you some background knowledge, AND and OR are defined in a separate language. It's an extension to the original robot language, where there's a logical operator abstract concept which has a notion of left and right, and then AND and OR, they both extend logical operator, add an alias and an OR, and semantics in the generator. And this action is defined for, this substitution is defined for logical operators, saying that if there is a logical operator will create a couple of actions. The parameter type is this time as a concept for logical operator. So typically and or. And here's a query that gives us all the concepts defined in this model, so in this language. So we take the logical operator concept, all its subconcepts in the model, such that these are not abstract. So we get concrete concepts that extend logical operator, and or in our case. We demand that the user types the alias of that logical operator, so either the word and or the word or. Here's a description, so that in the completion menu there's some more information. Well, and or in our case, so not really much. This is the name of the concept. Well, and then here's the substitution code that creates a new initialized instance of whatever the selected concept is, and well, assigns the left and right child and returns it. Now notice we could use a node factory here as well to save this copying code here. So let's do it. So we'll create a new node factory. Now we get logical operator. So whenever a logical operator is created and the instance of the sample node is also logical operator, so we copy new node left is now back to here. Now we should no longer need these. Now to properly utilize the factory we need to provide the sample node into the initializer here. So we have to provide the current target node, and that should do the trick. So now when you type AND, the left and right parts of the condition are preserved, and the other way around as well. Well, and the last thing I want to show you here, wrapping. This is somewhat similar to what you can do in Java when you type a type, like integer for example, int, and it will create a local variable declaration statement out of it. So I didn't have to say I want a local variable declaration statement. I only typed int, which is a type, right? And it is available in the completion menu. I can type int. It is available here. Although, in reality, an int type is not valid here. It can't be, a type can't be just a statement in a method body. It's not a statement. But there is a wrapper that, as soon as you type int, detects that there is a type in a place where a statement is required, and will wrap it in a defined statement. We can do the same in the robot language, although here it's more artificial example. You can type logical expression and it will be automatically wrapped in an if statement. So if I do control space, I can see stuff like wall ahead, which is a logical expression. It can't be placed as a command in the robot script. But if I pick wall ahead, for example, it will create an if statement with wall ahead as a condition. See, here it is. And I could, in the same way, I could try another one. Heading south, for example. And it will create an if statement for me. So this is a job for wrappers. So here's the one that we've been using here. So it's a substitution action. We substitute an empty line. So if we are on an empty line, we'll create an if statement by wrapping logical expression. So now logical expressions become available in completion menu on an empty line. And if you type a logical expression, then this code is invoked to wrap it. Well, here we create an if statement, set condition to the logical expression, and return the if statement. And that's it. Okay, so you've seen how actions can make your editor more dynamic. Okay, that was it. Thanks for watching. In the next episode, we'll talk about intentions. Goodbye.